All right, so let's get started. It's only 2 weeks left now of the quarter. So you handed in the reports Friday, I hope. This week will be quite a lot on the finalizing the last part of the project, I'm sure. And also to do the presentation and the oral exams and all these things. When it comes to the course, the material left is a presentation on Wi-Fi, not a complete presentation, but the most important parts and how that connects to what we have talked about in more general when it comes to medium access, for instance, and other things. And then a lecture on security, introduction to network security. And then basically it's a little bit of wrap up, maybe things that we didn't have time to talk about in enough details, review and things like that, and then that's it. So there's not so much new stuff coming up now. The Wi-Fi stuff here is a little bit of see how all ideas that we already talked about are implemented in a real system. Security will be new, of course. But yeah, not a whole lot of new left in the course. But to talk a little bit, the topic of today then is Wi-Fi, or actually it's the IEEE 802.11 standards. But before we start that, let's talk a little bit about review that's relevant for today. Channelization is on how to split a medium into different types of channels. And we use this, for instance, in Wi-Fi. The idea is that the channel resource is a rectangle in a time frequency plane. So if we have, say, frequency along this axis and time along this axis, the radio resource we have, our channel resource, is this rectangle. So what we want to do then is to squeeze in signals into this space, signals that are confined in time and frequency to this space. And then this can be done if it's only for one user of this. It's easy, we just use the whole bandwidth the whole time. But if we need to share this radio resource, this channel resource among different transmitters, we can split this into time, or we can split it into frequency, or we can split it into code. It's called time division, frequency division, code division. Frequency and time division is the easiest thing. So frequency channels, we basically split the bandwidth into two halves, and then we have two channels. Or if we do time division, we can split the time in, say, okay, happen to be 3 slots here. Then we have time divisions. We hand out time slots to the different users. Or we have a hybrid of this where we split both in time and frequency, and maybe this upper block here is handed out as one channel to one user, say. So actually this hybrid solutions is what you see in modern cellular systems. Actually all cellular systems also. So we have more bandwidth than is, with bandwidth and time, and we hand that out to the different users in different ways. So then a natural question, there's been a lot of debate about this, which one of these is the most efficient one, which one should we select? And the simple answer to that is that on a theoretical level, they are all equivalent, so there is not one which is better than the other. On a practical level, it depends, because in the isolation that we did here in time and frequency, typically one has to put in some guard intervals, maybe in time, like this, where we cannot use the channel for a short period of time, and this has to do with the propagation delays and so forth over the channel. And we also need probably to put in some guard intervals here, small frequency buffers between the different channels. Guard intervals in frequency when we cannot use the channel for this. And this has to do with imperfect filtering and things like that. So there are many practical constraints to this, which somehow favors one type compared to the others. But that has to do with propagation delays of the channels, the amount of money you want to put in your filters and so forth. So it's not a clear view there. But what I would like you to remember is that there is no theoretical basis for selecting one or the other if one ignores all these practical aspects. Okay. Then we talked about LAN protocols, and we talked a little bit about Ethernet last time, and in particular we talked also about the IEEE 802 family of protocols and standards. And in the OSI model, if we think about that, the lowest one is the physical one, and then there is the data link layer, and then there are network layers and things above it, right? But the IEEE 802 standards, they are link layer protocols and physical layer protocols. I don't know why it keeps on. Sorry for that. I don't know how to shut it off now. Anyway, so the upper layer in 802.11 is this LLC, or link layer control. And below that is a number of MAC protocols. We have here, which is known as Ethernet also. We have Wi-Fi that we will talk about today, and there is a bunch of others. And then below these is a bunch of physical layers also. So 802.3 is Ethernet. It's very common, as you know. And they're a slightly different and earlier version called Dixie Ethernet or Ethernet 2, or in the book it's also called Standard Ethernet, which is heavily used in practice also today. But anyways, yeah, okay, one more thing. We talked about bridges or switches, basically the same thing in this course at least. And used to connect different LANs such that station can perceive the connected LANs as a single LAN. Transparent means that these bridges, if this would be, this is an Ethernet switch, and if I connect computers to this one, the computers will, or the host will not communicate directly with the switch. They won't notice that it is there. It just takes care of enabling connectivity between the ports. So it's transparent in that sense. And it creates, these bridges creates forwarding tables. So a packet coming in one port here should go out in another port, ideally. And to create that table, it does that, the bridge does that by listening to the traffic that comes in to it. And by that figuring out which host with what MAC addresses is connected to which port. And then one can form these forwarding or routing tables. Then we talked very briefly about that there is a protocol called spanning tree protocols, which is used to create the logical topology, which is free of loops. Because otherwise this simple idea about building up the forwarding table by listening to the MAC addresses of the data coming in on different ports, it will create problems. Let's see if we can maybe spend a few words on that today, or we'll take it next week perhaps. Okay, so let's get started then. Up to now, we basically talked about, when we talked about communications and so forth, we've been staying in the wired domains. We haven't talked so much about wireless. Every now and then I mention a few things about it. But what is wireless is very nice, in particular because you don't have to have a cable, which is nice when you have, of course, sometimes you're forced to have wireless when you have handheld devices that you move around with, or if you have, for instance, communication between cars or trucks or whatever that's driving around, when there is inherently not possible to do wired networking. So this is clearly compelling. Okay, so what is the problems with wireless? And basically there are two things. First of all, the attenuation of the signal over a wireless channel is quite dramatic, I would say. So the power, the output power, the power of the transmitted signal decays quite rapidly in space. At least typically, if it's free space, the power decays as the square of the distance. Okay, And this means also, and also when there is complicated propagation environments, for instance, like what we are right now. So the Wi-Fi card here, I don't know where the access point is, but suppose I would like to communicate with the access point here, or with the base station, which I happens to know there is a base station on the roof of the mechanical engineering building over there. If I want to communicate with that, there is not a direct line of path, line of sight path between my device and the receiver, right? So the signal needs to bounce off objects, maybe this big wall over here, or will be diffracted over the rooftop to the base station and so forth. And all of these interactions, the bouncing, the refraction over rooftop and so forth, then the channel, the signal strength is then decaying also due to this. And moreover, when there is multipath transmission, where there is maybe a direct path and then a reflection in a wall or something like that, could create this type of interference patterns where sometimes there is constructive interference between two paths where the signal power actually goes up, but there could also be situations where the interference pattern is so that the signal strength goes down to zero even. So the signal strength varies quite a lot in space, and this is called signal fading. So these are problems in actually that the transmitted signal is not always received by due to bad propagation, right? The second thing is that it's a broadcast medium, so every transmitter generates interference to all other transmitters. So there is a severe interference problem in some cases. And then from a pure security point of view, it's easy to eavesdrop on signals that are transmitted in the air. It's very easy to do this. So one has to be a little bit more concerned about cryptography and things like this. And the final thing is that the spectrum, the radio channels, or the spectrum, the part of the radio spectrum which is useful, is quite congested. There are many systems that compete for this. So one has to be very, very bandwidth efficient in wireless. Otherwise it will be too expensive. Okay, so when it comes to mobile access to the internet, there are two main technologies. So if this is now cellular, so that's one thing. In particular for long range communications is this, that, okay, there are satellite systems also for really long range. If you're on a ship at sea or in an airplane, for instance, typically the connectivity to the internet is via satellites. But if you're on in a area where there is a fair amount of people, cellular is the go-to thing. And of course, if you're indoors and so forth, Wi-Fi is the dominating means of access to the internet. And today we will talk about Wi-Fi. And actually, before I start to say that, Wi-Fi is not actually equivalent to this IEEE 802.11. It's a bunch of standards for wireless LANs, but Wi-Fi is actually an industry association, the Wi-Fi Alliance, that had put up some specifications to ensure interoperability between different devices. And the thing is, why is this needed is because in the Wi-Fi standards, there are almost a countless number of variations you can have in a device. And a single device cannot fully implement all possibilities that the standard allows for. So the Wi-Fi Alliance, what they have done is they have cut out a subset of the standard and said, okay, everything that has fulfilled these requirements, get a Wi-Fi stamp on it. And then you know you can buy a Wi-Fi thing from Cisco and a Wi-Fi thing from Netgear, and you know that they will be able to talk to each other. Right. Okay, but anyway, so what was the starting point of this? Well, in the 80s, there was some spectrum that was released, and remember now that wireless requires spectrum, and spectrum is handed out by the authorities. It's like Post- and Telestyrelsen in Sweden. There are other agencies like the FCC in the US that hands out this spectrum. So they handed out some spectrum around, around 900, 2.4 gigahertz, around 5.7 gigahertz, like this. And then this was open for communication for many different types of systems, as long as you fulfilled some basic requirements. So then IEEE started to work on a wireless local area network technology called 802.11. Started in 91, first release of the standard was in 1997. And now it's been evolving to a very, very complex standard. So, and since there is constant evolution of this, which means that whatever book you pick up, it's likely outdated, right? Even if it was released last year, it's probably outdated today. So if one wants to look at the latest and greatest, one has to download the standard document. And you can do this, it's free of charge. It's, I did that yesterday. 3,500 plus pages. Okay, so it's not something that you just read like that from cover to cover. And the thing is that out of these 3,500 pages, not all of them are used at all, right? So there's certain parts which are today available in products, but for legacy reasons, these have been once they in the standard, they don't leave, basically. Okay. So if one looks at how this works, so this is a screenshot from my laptop. Maybe not this year. I have a new laptop now. So, but anyways, if you look at there's similar things on Windows, I'm sure. But there are a few things here. There's something called the SSID, the security, BSS ID, channels, country code, RSSI, noise transfer rate, physical mode, and MCS index. So what does all of this mean? And that's a few things we will touch on today, right? So let's start dissecting this a little bit. Start with a few definitions. So this might be a little bit unclear on this slide, but we'll try to justify it as we go along. So there is something called a basic service set, or BSS. And there is an identification of that called a BSS ID. And so what is a basic service set? Well, it's a group of stations. And stations, think of that as transmitters, receivers, right? So this iPad is a station, this laptop is a station, this is a station. The access point, wherever it is also a station. But anyways, a basic service set is a group of these stations that coordinate their access somehow. They can communicate and they coordinate their actions, essentially. There's something called infrastructure network, and we will make that clear a little bit later. But basically, an infrastructure network is a network where you do have an access point, because it turns out that Wi-Fi also supports networks where you don't have access points. Okay, and for these, which are the common ones, I would say, right? So, I mean, here since I'm connected to Edirome here, it's an infrastructure network. So, in that case, the BSS ID is the access point MAC address, which is one of these familiar, if you're starting to become familiar, it's a 48-bit address, like the physical MAC address you have on an Ethernet card. The same type of structure of this. So in my old laptop, this was when I connected to Edirome way back, it was this MAC address of the closest AP when I took the screenshot. Okay. These basic service sets are located in a physical area, which we call the basic service area. So basically, it could be maybe a number of rooms in this building, or a floor, or whatever. It could also be that it's 2 floors, but in a certain part of the building. Wherever you have coverage from an access point is this service area. Now, stations which are in this BSS, they can communicate with each other. And also, as you know, there are many BSS could be coexist, right? So if you search for a Wi-Fi network, you get a bunch of them typically, right? So many competing networks in the same area. As a matter of fact, an access point could also have many BSSs in them. It could have, for instance, in a home, it's common to have like your basic encrypted network, and maybe you have a guest network also, but they come from the same access point. Okay, now if these basic service areas could be fairly small, so if you want to cover an extended area like a campus or a big building, you need many of these access points. So you connect all these access points into a bigger entity called an extended service set, ESS. And this is then identified by an SSID, which is this network name. So if we go back here, the SSID eduroam here is basically available over the whole entire campus here, right? But there is not a single access point that coordinates this, and many access points. But the access point that I happens to be closest to at the moment is this one. Okay, so this is the MAC address of closest IP access point. I mean closest in the sense that this is the one that I'm connected to, and this is like the extended service set ID, I would say, or. Okay, so eduroam is the network, while the BSS ID is the access point I'm currently connected to. If I move to some other part, I will still be on eduroam, but with another access point. Okay, so how these basic service sets are interconnected by something called a distribution system. This is typically like an Ethernet LAN or something like that, but something that connects the different access points together. And each basic service set is then like a cell, if we think about the cellular system, and the stations in this BSS can then communicate with this access point. And then to the distribution systems, one typically have these devices called portals. Think of them as routers that connects the distribution system to the internet. Now, communication is also possible outside the context of a BSS, which is this ad hoc mode, which is used, for instance, in 11P. Remember that this was the technology used for communication between vehicles at the moment for traffic safety and traffic efficiency. So one doesn't necessarily have to have a basic service set to communicate. Okay, so that was a lot of words. Let's have some pictures here. So there are basically two types of basic service sets. One which is independent, like this, where there's a number of stations here, A, B, C, and D. They all have Wi-Fi cards in them, but there is no access point. Okay, so this, regardless, these can form then a network to start to communicate with each other if they need to. So maybe there's a, I don't know, for some reason. This is not super common, but it can be done. So this is called an independent basic service set here, so or IBSS. And this ad hoc can also be done without forming a basic service set, and then it's called communication outside the context of BSS or OCB. Okay, so I won't talk much more about this than this. It's just that this is a possibility. You can connect with each other like this. So this is the more common thing, which is called an infrastructure network. And infrastructure, that means that we have an access point. Okay. Once we have an access point, it's an infrastructure network. And these access points are typically mounted on the wall or something like that. They are connected to each other over this distribution system. This is often Ethernet. For instance, Ethernet, but it could be other things also. And then there are these portal devices, and if we have a gateway, another way to say that we have a router, which is then connected to the internet, or we can have different types of service which are directly connected to your Ethernet backbone here, or distribution system. You can have that also. Okay, so this is then the back end of the things, and then we have, in this case, two basic service sets, basic service set A and basic service set B, and they are connected with this distribution system. So together, these two basic service sets forms an extended service set. Okay, so for instance, we can think of this as being eduroam, right? And then this happens to be whatever access point is closest to us is what we are connected to. If you move over to other part of the campus, we're connected to this one. Okay, so then how is communication done here? Well, I mean, if A1 wants to talk to A2, actually this communications goes via the access point. So even though it might be possible to communicate directly here, the data frame from A1 to A2 actually goes first to the access point, and then from the access point down to A2. This is similar to what is in cellular also. You communicate directly with the base station and then to the other device. We can also have communications from A1 to B1, for instance, and then it goes first to the access point, then through the distribution system to another access point, and then down to B1. Okay, and then of course there is maybe the most common type of communication is from a station to the internet and back, and then the frame first goes from the station to the access point via the distribution system to the router, and from the router further into the network. Okay. Any questions so far? No. Okay. Yeah. So maybe I should say a few things. One thing that I wanted to say. So an access point. This is basically a bridge between wireless and, say, a wired system. If we have, if the distribution system here is Ethernet, as it usually is, right? Which means that frames needs to be converted from Ethernet frames to Wi-Fi frames in this device. So it's a link layer bridge. Okay. Yes. Okay. So again, base station or stations within this BSS, they can communicate directly with each other. So the distribution system then performs distribution services. Maybe this is not super important, but basically from the link layer point of view, in the stations, it doesn't know the existence of the distribution system. It just provides connectivity between the different stations. This ESS that looks like a single BSS to the LLC layer also, so it's not even visible for the stations above for the LSC layers in the stations. So infrastructure services. So when we have these access points, before you can even start to communicate with the internet, when you open up your laptop for the first time in a new area, is that you need to log on to the network, right? If you haven't done it before. So there is something called association. It's when a station selects an access point and then establish an association with it. And it usually needs some type of password to do this. So this will be the equivalent of this. Suppose that this laptop is connected to this cable here. Like now it's not associated, now it's associated, right? So it's like connecting to the network. And there is a procedure for doing that. And on Wi-Fi, of course, there is some security involved in this. So most network, many networks at least, you need a network ID, password to do this. Once you have done the association, then you can start to send and receive frames from the access point, and via the distribution system, you might be able to access the internet also. There is a reassociation service, and that is when you move from one access point to another. So if you're a station like this, and there is an access point here, access point 1, there is an access point 2, and then there is a somewhere in between when you're connected here and the station goes over to the other side here, then it switches to communicate with that access point. So this is called reassociation, where you associated to an access point, but when you move, you break that association in a way and then associate to another access point. So this is reassociation. And disassociation basically is when an access point kicks out the station, or the station says, well, I'm no longer interested in being connected to your network. Then there is a authentication service, and this is done to make sure that we can know what station, when data is sent from a station, that we can actually at the receiving end make sure that it comes from that station and from no one else. So this is a security metric. We'll talk more about authentication in the next lecture. Privacy service is to keep content secret. So basically, if we have like a bad station here that listens in to that communication, it will not be able to decode the bits which are transmitted here. So think of this as some type of cryptography. We'll talk more about that in the next lecture also. So any questions so far? Okay. Medium access control then. So we talked about medium access control, and so basically what is the main responsibility of this? Well, it's channel access is the biggest thing. So sharing the wireless channel is the big thing. Then of course there is addressing, formatting, error checking and so forth. There is also fragmentation and reassembly of big frames into smaller frames. All of these are transparent for the layer above it. There's some security services, authentication and confidentiality, and then there is some management, like roaming means like going between different access points, and then some power management also. But let's talk about the medium access control. And there are two services which are standardized in 11p. One which is the contention service, and this is the common one, or I would say almost the only one which is implemented in practice. And what it means is that, okay, so here, remember here, so here we have the medium access control. What type of service do we provide to the layer above it? A contention service basically means best effort. Whatever frames goes down here might come up to the intended receiver, but there is no guarantee. So best effort means that I will try to do my best to deliver frames. I promise nothing. Then there is a contention-free service also, and it basically organizes, as we will see later on, medium access control in 802.11 is this carry sense multiple access with collision avoidance. It's some type of random access type of mechanism. One can also do more like a controlled access communications through this contention-free service. And we won't talk much about it because it's not rarely used in practice. I don't know if it's ever used in practice, but it's in the standard. Anyways, the names of these two services, the contention-free service is called Point Coordination Function, PCF. Okay, from a protocol point of view, actually PCF lives over this main workhorse of Wi-Fi, which is called Distributed Coordinating Function, or DCF. And this one uses carrier sense multiple access with collision avoidance. And we'll talk more about what that actually means. And then there is a physical layer below it. All right? Okay. So medium access then. I mean, here is the tricky thing, right? Wireless is a shared medium, and it's a very poorly isolated medium. So whatever Wi-Fi frames which are generated in this room and transmitted is likely to interfere to some level other Wi-Fi transmissions which are ongoing, maybe hundreds of meters from here. Okay. So and also we would like this to be use the spectrum efficiently here also. So 802.11 was chosen to use carrier sense multiple access with collision avoidance. And basically when one selected this, one was primarily interested in having something which had low cost. Okay, so it's not the most efficient way to do things, but it works very well if there is not a high load on the channel, so not a lot of traffic ongoing, and it's also relatively cheap to implement. And also it's similar to what's done on Ethernet. And all of these factors together somehow led to that the IEEE people chose carrier sense multiple access for its wireless LAN. Right? So anyways, now that decision has been made, and it's proven to be quite successful in the sense that there are many Wi-Fi devices out there, but it might not always be the optimal one, especially not when there is a lot of traffic ongoing. Okay, so if you remember from Ethernet, so what does Ethernet use medium access? Do you remember? Yes?
CSMA CD?
Yeah, exactly. So it's the Ethernet is CSMA, carrier sense multiple access. Listen before you talk, but with collision detection. So collision detection, however, it's a great idea if you can do it. Okay? So collision detection essentially means that when you transmit the frame, you also monitor the medium to see whether there is a competing frame causing a collision. And if so, you stop transmitting, you try again. So you don't keep on colliding for a long period of time. The problem is that it's very hard to do this in wireless. And in the book, they have an explanation for this, which is, in my view, completely bogus. So don't read that, you know. But here's the thing. And the thing is that the transmitted signal has much higher power than the received signal, typically, right? And why is this? Well, it's because if I would like to communicate, so here we have distance on this axis, and here we have power. Okay. So if I'm at the transmitter, transmit with a certain power, it would decay. Now, so this is more in the in a log-log plot. So this is power in dB. It turns out that in a log-log plot, it's more like a linear decay, like this. Okay, and what we lose here, typically it's minus 20 dB per decade. So we lose 20 dB, it means a factor of 100 for each, from going from 10 meters to 100 meters, we lose 90% of the power. Okay. So power drops down quite a lot. Okay. And then there is some type of noise floor here. And we're able to communicate as long as the signal-to-noise ratio, which is since this is in dB, it's the difference between these two things. It's the ratio of the powers. So as long as the SNR here in dB is large enough, we can communicate. Okay, and so how much power we need for this to happen? Okay, so suppose this is the smallest SNR we need for this to work. Then the smallest receive power for this to work is called the sensitivity. Okay, so the sensitivity is the smallest receive power we can have for this to work, while the transmit power we have here is the maximum power we allow to transmit. And the difference between this, it could easily be in the axis of 100 dB. Okay, so the difference between the transmit power, when we transmit that maximum power, maximum allowed power, and the smallest power we need in order to communicate, this could be 100 dB. Okay, so is 100 dB, is that a lot? Yeah, it's a lot. 100 dB corresponds to 10 to the power of 10, 100 divided by 10, or 10 to the 10 difference between these two powers. Okay, so it's a factor of 10 billion, 10 miljarder, in transmit power and minimum receive power. Okay, so suppose we can receive, now this is the wrong units, but suppose the receive signal is 1 watt, then the transmit power would be 10 gigawatts, right? You can see that will be a slight difference between, it would be easy to burn out the receiving circuitry if we don't protect it. Okay. So in wireless, it's hard to listen to the channel when we transmit. Therefore, no collision detection. Questions? Okay. So then, if we go back here to look a little bit about the powers that we have.
There's a window, Skype.
Oh, great. So Microsoft took over the Skype thing. I don't know what happened to the software. Okay, thank you. Okay, so now I lost all my annotation also. But here, this number here is the current received power. Okay, 1 dBm is equal to 1 milliwatt. So in this case, it's minus 75 dBm. Okay, so it's 10 to the minus 75 divided by 10, 10 to the minus 7.5 milliwatts. That's not a whole lot of power, right? Okay, so this is the current received power in this screenshot. The noise, however, luckily is much smaller, right? So it's at 90 dB. So this is 10 to the minus 9 milliwatts. Okay, so the SNR is then the difference between these two numbers, minus 90 and 75. So what is that? It's 15 dB, right? So 15 decibels, or 10 to the 1.5. That's, you know, it's not quite 100, but, you know, more than 10. So that's the difference between in this plot, the current received power and the noise floor in this case. So when you move closer to the access point, better SNR, right? Further away, lower SNR. And this has an impact later on, as we will see, on which data rate you can get out of the system. Okay, so let's take 15 minutes.